Hello and welcome to Dunia's Alchemy. I've condensed the whole topic from the specification into two separate videos. The first 3 points, as you can see here, are required for all tiers: foundation, higher and triple. The second part will be for triple students only, and this will be in another video linked in the description. This is a GCSE Chemistry lesson on a 2-part series for chemical analysis. The video breakdown is below. We're going to look at purity and formulations, tests for gases, and chromatography required practical. So let's begin. Let's say you go to a supermarket and then you ask someone for some pure water. Most likely, what they will do is hand you something that looks like this. But the question is that actually pure water? So if you were to look at the back on a lot of the water bottles that we drink from, you're going to see that there are dissolved ions inside. So then I'm going to pose the question again. Is it really pure? The answer is yeah and no, depending on what you mean by pure. There are 2 definitions of a pure substance that you need to know. The first one is the everyday definition, and that means a substance with nothing added to it. That's what that person at the supermarket would have most likely given you. They wouldn't give you juice or any other thing. It would be water, because that means that water doesn't have something else added to it. However, the chemical definition is when a substance contains only one element or a compound, meaning water is H2O. It should have only H2O molecules inside the water. It shouldn't have anything else. If a substance is chemically pure, it will melt and boil at a specific temperature. So that means it's going to have one value. So water has a melting point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. However, if there are impurities inside it, that's when it becomes a range. Impurities do 2 things. They lower the melting point and increase the boiling point. And therefore, you've increased the melting and boiling point ranges. A formulation is a useful product designed by mixing components in measured quantities, so the product has the required properties. Examples of formulations are food, medicines, fertilizers, cosmetics, paints, fuels, and metal alloys. There are measured quantities, meaning very specific amounts that are added in order to make a formulation. You don't just throw things together and create a mixture. That does not qualify as a formulation. We're now going to look at 4 different gases and the test for each one. So let's begin. The first one is hydrogen. And with hydrogen, you put a burning splint or a lit splint held over the end of a test tube. And if you see it burn rapidly with that famous squeaky pop sound, then you know you have hydrogen. The oxygen, you have a glowing splint, and this is inserted into a test tube of gas. This splint relights in oxygen. As you can see over here, you have the glowing splint being exposed to the oxygen, and it starts to relight. So you see a flame evolving at the end of that wooden splint. Third gas is carbon dioxide. This gas is shaken or bubbled through lime water, which is also known as calcium hydroxide. And the result is that the lime water turns milky or cloudy if there is carbon dioxide present. And last but not least is chlorine. Damp litmus paper is put into the gas, and if that litmus paper is bleached, that shows you have chlorine there. This is a very famous exam question, the required practical steps for chromatography. I have given you a gap fill task over here along with the word bank, so feel free to pause the video and fill in the sentences. Draw the baseline onto the paper using pencil. I've highlighted this because it's extremely important. The pencil graphite is insoluble and it will not dissolve. That's why we use it. Apply a small spot of sample onto the baseline and allow it to dry. Small spots produce clearer separation. Pour a small depth of solvent into a beaker, keeping it below the baseline. Again, very, very important. Make sure that your liquid, the solvent that you add in, is below the baseline. Common solvents are water and ethanol. Place the paper into the beaker by suspending it vertically. Ensure the baseline stays above the solvent and the paper does not touch the sides. You can cover it with a lid or watch glass if possible. This will prevent evaporation and also improves accuracy. Allow the solvent to travel. The solvent moves up the paper by capillary action. Substances separate because they have different solubilities and different attractions to the paper. We're going to look at this shortly. Remove paper before solvent reaches the top. Immediately mark the solvent front in pencil. This is a critical exam point. Dry and observe results. Each spot represents a different substance, and you're going to see spots appearing at different heights. From here as well, you can mention calculating RF values, which we're also going to look at very soon. So let's have a look at the features on the chromatography paper. Firstly, you have your pencil baseline, and then you also have a small spot or your dye or ink that you place onto that pencil baseline. When we say shallow water, we essentially mean below the baseline. So make sure that the liquid that you fill into your beaker is sitting below the pencil baseline. Another thing is, once you allow the liquid to soak through the paper, make sure you don't let it go all the way to the edge, and that's where you, when it gets close to the edge, essentially, that's called your solvent front. There are two key words that you need to know, and this is your stationary phase and your mobile phase. As the name suggests, in stationary phase, it's the phase that remains fixed in place during the separation process. So this does not move, and in this case, this would be your chromatography paper. Your mobile phase is the fluid or the liquid that does move through the system, and that carries the sample with it, and this is our water. In other cases, it could also be ethanol. And then finally, this could be the result of two different spots you have after the separation. So let's have a look at analysing our results. Firstly, the fact that you see two spots is proof that the original spot or the original dye is not pure. The fact that the yellow dye is further up the paper, that means it was more soluble in the mobile phase. It travelled further with the liquid, whereas the red dye has not travelled as far. So this was more attracted to the stationary phase, which, if you remember, was your chromatography paper. So it had less affinity or attraction towards the mobile phase. So comparatively, the yellow spot prefers the mobile phase more than the red spot, which prefers the stationary phase. So now we can put these in actual numerical values. By calculating RF, I call it distance travelled by spot divided by distance travelled by liquid. So let's have a look at that a little bit more in detail. So again, I've shown it to you over here. RF is distance travelled by the dye or the spot divided by the distance travelled by solvent. So if I was to grab a ruler and focus on the red spot, what I would do is I would find however many centimeters it is from the pencil baseline to the center. And let's say, for example, the dye distance was only 2 centimeters. And then I would calculate how much the solvent has travelled. And this value could have been 6 centimeters. So that means my RF value for the red spot would be 2 divided by 6, and that would give you 0.33. RF has no units because the units cancel out. This is our video complete. We've had a look at purity and formulations, test for gases, and finally required practical for chromatography. As usual, make sure to do the 3-2-1, share it with 3 others, give it 2 clicks, like and subscribe, and finally leave 1 comment. Have a great one.